So I'm covering the future of our sun. Before we talk about the future, or basically how it approaches its death, we'll talk about just understand stars a little bit. As some of you probably already know, from our trip to the GDC, a star is born from a nebula, a cloud of collapsing gas or dust, and it's the most abundant gas inside it is hydrogen, as it's the most abundant gas in the universe. And the fusion of these hydrogen atoms into helium is what powers our sun. Basically, releases a lot of energy in the form of heat and light during the fusion. That all occurs in the very core of the sun. And just for 1 second of sun power, which in turn is the heat and light we experience every day, is needed 600 million tons of hydrogen. I know that contradicts what the last person said. Source is NASA, but so that's, roughly 6 times 10 to the power 8 tons. If you want in kilos, just add 4 to the 8. And for comparison, Earth weighs, as you can see, 1.35 times 10 to the power 21. So to use the Earth's mass in hydrogen would take 70,000 years to give us that much, to use up all that hydrogen. And currently it's about halfway through all of the hydrogen at the very, very core of its mass. And once it goes through all that hydrogen, it will start to make its way off the main sequence and become a red giant. So, as I said, it's about a middle-aged star. It's 4.6 billion years old. It's got about another 6 billion years to go before our lovely star just goes. So here we can see, here we can see that's where it is on the main sequence, just down here, and you can see it's class G, yellow dwarf, so it's actually quite an average size star, quite small compared to other stars. And these stars don't have enough mass to become a supernova. You need about 8+ solar masses to become a supernova, so instead it will just follow this track called the red giant branch here, and just leave the main sequence, getting larger, becoming a red giant. Sorry, back here, as I said, that the sun was 4.6 billion years old. How that is actually aged is by rather unintuitively looking away from the sun towards Earth. We take rock samples, and judging by the oldest rock samples, we can deduce that it's 4.6 billion years old because all the elements in our solar system would probably form around from the same nebula. So going back here. So in about 6 billion years, it will have depleted all of its hydrogen. So it will start expanding as some of its mass has decreased. So there'll be inward gravitational pressure as it's used all of its hydrogen, and it will start expanding to match that pressure gradient. So what's happened here is all the hydrogen's been used up, and now it's all helium in this core. And here we've got a hydrogen shell, so more pressure is actually increasing there as there's more gravitational force towards the center of it. And eventually a second phase of hydrogen fusion will occur, and just occurring in this room here, not actually in the core. There's no more hydrogen in the core. As this happens, helium is just being dumped in the core, so more and more helium is being fused actually in the core, because there's still obviously quite a lot of pressure in there. That's creating carbon and oxygen, which is actually how most of the carbon and oxygen is produced. low on helium, and its heat will reduce. It's already expanded quite a lot, probably to the closest 3 planets, Mercury, Venus, and Earth. So goodbye to Earth, basically. If we don't melt or disintegrate. So as this heat's lowering, it's no longer actually keeping any of its elements in the gas phase in the outer layer. As you can see here, these are all gases at the moment, just kept in the phase by the heat produced by the sun, but they're no longer kept in that phase as it cools and expands. So they're actually condensing out and becoming solid particles with whatever was produced in the core and then pushed out. So as these are leaving, these elements, they actually, doesn't sound so bad, it's just kicking out elements, but it actually takes some of the gas with it. So it's actually pulsating and blowing off layers of its atmosphere. So in large pulses, which will probably extend way beyond the 3 planets that it's already enveloped. At this point, it's blown off all its layers, which takes about 100 million years or so. And when it's got no more layers to blow off, no more gas to keep in the gas phase, all that's left is a big cloud of gas and dust, as we know as a nebula. Technically a planetary nebula, which is illuminated by what's left of the star, which is just a bright glowing white hot core. It's just a white dwarf, and all that's left in that white dwarf is solid carbon now, because of the pressure has made it solid, or not exactly solid because it's still quite hot, but due to the fact that it is pretty much just pure carbon, it will actually be a giant space diamond about the size of the Earth. And at the moment, when it's a white dwarf, there's no more fusion is happening. So it's not producing any more heat. It's just staying bright from what was left over of its heat, and it will slowly cool to match the temperature of the universe. At which point, I think it's termed a brown dwarf. And that's it. Questions?
You know, you said something about 70,000 years or something for
Yep.
the Earth to burn. I was wondering what was that? I was really thinking about that.
Yeah, so here, I mean, it's just saying that the Earth's mass in hydrogen, which is 1.35 times 10 to the 21 tons, or times to 24 kilos, it would take 70,000 years to fuse that much hydrogen at the core to actually give us the energy that we need. Yeah. Any more questions?
Yes. What gives a red giant its red hue?
The colour?
Yes.
So if we go back to, this is a good slide to show that. It's actually just by the surface temperature and its spectral class. So as this is the effective temperature, as that increases, its colour will change. So you see when it moves off this track and up here, it's it will go. Sorry, as the temperature decreases, it will go up here to the red giant phase, and as it's cooling in its red giant phase, getting bigger, and it can no longer maintain the same luminosity relative to its mass, it will go red because that temperature, basically. Any questions?
No, I think we've got to move on.
Cool.